In continuing our discussion as it pertains to different probability types, in this lecture we're going to discuss the Poisson distribution. And as you can see by looking at the way the distribution is graphed, unlike the normal distribution and similar to that of the binomial distribution, the Poisson distribution integral is going to differentiate depending on the value of lambda, and the value of lambda will be derived from the phenomenon which is being observed. We're going to be taking a look at the definition of this distribution type. We're going to go over its application, and we're going to do a couple of examples in the R programming language. So the definition of the Poisson distribution. In probability theory and statistics, the Poisson distribution is a discrete probability distribution that expresses the probability of a given number of events occurring in a fixed interval of time. And that is, if these events occur with a known constant mean rate and independently of the time since the last event. This will become evident as we go through the examples. It can also be used for the number of events in other types of intervals than time and in dimensions greater than 1. So the Poisson distribution applies to occurrences over a specified interval. The random variable x is the number of occurrences of the event in an interval. So let's take a look at the internal symbolic attributes of the Poisson distribution. Mean, or lambda, lowercase lambda, is the average number of occurrences of the event over the interval, okay? And x is the number of occurrences of the event over the interval. So here's a couple of requirements. And again, these are similar to that of the binomial distribution. The random variable x is the number of occurrences of an event over some interval. The occurrences must be random. The occurrences must be independent from each other. The occurrences must be uniformly distributed over the interval being used. It cannot be seasonal. All right, so we're assuming that each occurrence is random, which means they're not impacting one another. And that also speaks to the next point. The occurrences must be independent from one another. So the occurrence of one event occurring is not going to impact the probability of another event occurring. And the uniform distribution over the interval being non-seasonal means that this is over a fixed period of time. We're not expecting some sort of seasonality to impact our outcome, whether we're looking at the underlying phenomenon at this point or another point in time. So here are some ways in which the Poisson distribution, though somewhat similar, does differ from the binomial distribution. The binomial distribution is affected by sample size n and probability p, where the Poisson distribution is affected only by the mean. In a binomial distribution, the possible values of random variable x are 0 and 1, but a Poisson distribution has possible x values of 0, 1, 2, 3 to infinity with no upper limit. Now, just to sort of make this clear in layman's terms, what this second bullet point is seeking to indicate is that with the binomial distribution, we only have as many occurrences as are being assessed. So if we flip a coin 7 times, we're either going to get 7 heads or 7 tails. What a Poisson distribution is different in that there is no upper limit. There's no set limit as to how many heads or tails you can get as based upon the trial size. And what this means will become clear as we move forward. So here's an example right here. Let's say that every Tuesday in spring for 8 hours, you have a webcam set up that films for bluebirds which frequent your garden. You've counted these bluebirds, and over the course of the season, have noticed an average of 12 bluebirds visiting your garden each day. What is the probability that exactly 8 bluebirds will visit your garden given the parameters of the experiment? So first we have to find the variables within the question which are pertinent to our research. So in this case, we're looking at the average being 12. So lambda is 12 bluebirds. And we want to know the probability that exactly 8 bluebirds will visit your garden given the parameters of the experiment. And as you can see, this is over the course of a season. So we're assuming that the phenomenon, whatever it is that we're observing or whatever it is that is the underlying phenomenon as it relates to generating these observations, will remain static across the season. So we're not looking at spring to summer, summer to winter, and so on and so forth. This is just a single season. All right? So exactly 8 bluebirds, given we typically see an average of 12 bluebirds every 8 hours that our webcam is set. So here is the corresponding R code. And as I mentioned in each video, and as is the case in each video, the code is in the video description below. So go ahead and get that if you want to follow along at home or try these examples out yourself. Sometimes it can be helpful because if you're in a course, you can change these variables or to whatever it is that you're working with to generate your own output to hopefully provide you with the answers for whatever questions or inquiries are necessary for your course. But in any event, here we have our x equals 8, lambda equals 12, and x equals 8 because we're looking for exactly 8 bluebirds, and the average is 12. Okay, so lambda is 12, x is 8, lambda is 12, x equals 8. All right, so if we enter this into R, this generates the result below. All right, so let's do that quickly. Let me get R set to go. There we are. So what is the probability that exactly 8 bluebirds will visit your garden given the parameters of the experiment? So exactly 8 bluebirds, x equals 8, lambda equals 12, because that's the number of bluebirds we expect to see every 8 hours that our webcam is set up and filming our garden. So this is our output here. It's 0.06552328. And if we multiply that value by 100, because we need to turn it to a percentage, we come to, assuming that the gears will turn, 6.552328. So what is the probability that exactly 8 bluebirds will visit your garden given the parameters of the experiment? It is 6.55%. All right. Back to our slides. So yeah, just move that decimal point over too, and then decide how you want to handle significant figures. But if we're working with 2 significant figures, it's 6.55%. That is the probability that we should expect to see exactly 8 bluebirds, given we typically see an average of 12 over the span of 8 hours. So what is the probability that exactly 0 bluebirds will visit? What is the probability that exactly 1 bluebird will visit? What is the probability that exactly 2 will visit? What is the probability that exactly 3 will visit? So we want to determine the probability of each of these events occurring. So in this case, we're going to use this function here, dpois, x equals 0, and then 3, lambda equals 12. And if you enter that into R and execute that code, this is your output. So right here, this is the probability of exactly 0 birds. This is the probability of exactly 1 bird. This is the probability of exactly 2 birds, and this is the probability of exactly 3 birds. And obviously, as you can see, these are in scientific notation. So let's take a different approach to this. Same scenario. But we're interested in the probability that 6 or less birds will visit your garden. 6 or less. So exactly 6 or 5 or 4 or 3 or 2 or 1 bird will visit the garden. So there's two ways that you could approach this. You could either use the sum function and then within it dpois, x equals 0 to 6, lambda equals 12, because again, we're still operating under the assumption that the experimental parameters hold, in that it's an average of 12 birds each session, or ppos, q equals 6, lambda equals 12, lower tail equals true, and lower tail equals true. It's, if you recall the lecture on the normal distribution, the same sort of methodology applies. So lower tail equals true. And this generates this value below. Either of these functions will generate this value below, which is 0.04582231. And if you move the decimal point over two places, that's 4.58. So what is the probability that 6 or less birds will visit your garden? That's 4.58% if we're working with two significant figures. And again, that means that we'll either expect to see 6 birds, 5 birds, 4 birds, 3 birds, 2 birds, 1 bird, or no bird at all over our 8-hour span of filming. What is the probability that more than 6 birds will visit your garden? So in this case, the probability that more than 6 birds will visit your garden. So not 6 or more, but more than 6. So 7 birds, 8 birds, 9 birds, 10 birds, 11, 12, 13, and so on and so forth to infinity. You could have infinite birds visit your garden with the way that these experiments are conducted. So just keep that in mind when you're structuring them. So what is the probability that more than 6 birds will visit your garden? It could be any number of birds, but it has to be greater than 6. Well, that is this function here, ppois, q equals 6, lambda equals 12, lower tail equals false because we're looking to the right. Again, same logic of methodology applies as it applied to the normal distribution. If you are unfamiliar with that, make sure you take a look. There's another video in the playlist as it relates to the normal distribution, which should make this clear. But in any event, that generates the result when this code is executed within R. It generates the result of 0.9541777. And if you were to move the decimal point over two places, that's 95.417. You could round that to 95.42 if you're doing two significant figures. So what is the probability that 6 bluebirds will visit your garden? Well, that is 95.42%. So that is it for this particular video. If you made it to the end, congratulations. I appreciate you stopping by, and I hope that you found this helpful in getting through your research or getting through your coursework. If you enjoyed what you saw in this video, please consider liking and subscribing, and all the best of luck. I hope you have a wonderful rest of the day. Take care.